We're going to begin this section with a problem. Consider a parallelogram determined by vectors u and v. So when we say a parallelogram is determined by two vectors, we mean that those two vectors correspond to two adjacent sides of the parallelogram. Now, because it's a parallelogram, you really only need two sides to know what the other two sides would be, right? Because the sides will be parallel. So I'll have one side over here that's parallel to vector v, and one side over here it's parallel to vector u. Okay? We want to find the area of this parallelogram. All right? So the area of the parallelogram, the area of the parallelogram is just going to be equal to the base of the parallelogram, the length of the base of the parallelogram, times the height of the parallelogram. Okay? Now, we could choose either side for the base. I could choose the side of vector v. I could have that. Imagine that's the base of the parallelogram. Or the side with vector u. I'm going to choose the side with vector u. So the length of this side is the length of u. So the norm of u is going to give me my base. So norm of u. Now to find the height, we want to be careful here. We want to measure the orthogonal distance. That is the distance that we would get if we go directly up, perpendicular to vector u, up to the top edge of the parallelogram. Okay, so this is meet vector u at a right angle. So this is going to be our height. Okay, and we could see that we have a right triangle here. So we could use some right triangle trigonometry to find the height of this side of the triangle, okay, which will also be the height of the parallelogram. And so using a little trigonometry, I notice that the height here, let's call it h, the height over the hypotenuse, which is just how long vector v is equal to sine of theta. Okay, I just used this angle here and got opposite over hypotenuse. Opposite is the height I want. Hypotenuse is the length of vector v. And so the height is just the norm of vector v times sine of the angle between the two vectors. All right? But hold up a moment. This formula looks familiar. We have norm of u, norm of v, sine of the angle between the vectors. In actuality, if we are in three-dimensional space, we have a simpler way to express this. Recall for vectors u and v in R3, the norm of the cross product of the vectors is equal to the norm of u times the norm of v times sine of the angle between vectors u and v. We discussed this at the beginning of this course. And so that means that in R3, I can find the area of the parallelogram determined by two vectors u and v by taking the norm of the cross product of the vectors. Okay, that is, the area of our parallelogram is equal to the norm of U cross V. Okay, let's see an example. Find the area of a parallelogram determined by vectors U, which is vector -2, 1, 3, and V, which is vector 1, 6, 2. Okay? So all we have to do is take the cross product of these two vectors, then take the norm of the cross product. That is going to give me the area of the parallelogram. Okay? So let's recall that the cross product of U and V, to find that, I think of a determinant, right, where the first row is ijk, the second row are the components of U, -2, 1, 3, and the third row are the components of V, 1, 6, 2. And so if I take the cross product, I'll do it rather quick, for I, the I component, I get 2 minus 18, so that's a -16. For the J component, I have -4 minus 3, so that's going to be -7. And for the K component, -12 minus 1, that's -13. So that's U cross V. To find the area, we want the norm of U cross V. So the norm of U cross V is going to be the square root of the sum of the squares of the components of the cross product. Okay, and if you do the arithmetic, you'll find that -16 squared plus -7 squared plus -13 squared, that is 474. So the area of the parallelogram determined by two vectors U and V is square root of 474. Okay? Now I want to do one more example. This example is going to be important. All right? Find the area of the parallelogram determined by vectors 2, -1, and 3, 4. Now, this one's interesting because for the last problem, we knew to find the area of the parallelogram, we just need to take the cross product of these two vectors. But these were three-dimensional vectors. They lived in R3. And so the cross product was well defined. These are two-dimensional vectors. The cross product isn't defined for two-dimensional vectors. So we can't use the same trick that we used up here. We can't just take the area of the norm of the cross product. or rather, we can't do it unless we do a little trick first. The cross product only works in three-dimensional space, but using a little creativity, we can actually move to three-dimensional space. So what I'm going to do is I'm going to embed these two-dimensional vectors into three-dimensional space. And that sounds fancy, but all I'm going to do is just keep the same vector with the same two components, just add a 0 at the end. Okay, same thing for vector 3, 4. Keep the x and y components the same, just add a 0 for the z component. Okay, that embeds the 2D vector in 3D space. Okay, both of these vectors live in the xy plane, which is exactly where they lived in two-dimensional space. We just didn't have a third dimension to work with. So it still lives in the same plane, the xy plane, where z equals 0. Okay, there's just a z component, so there could be things going on above them, there could be things going on below them, but otherwise, the two vectors are the same. Okay, and now that they live in three-dimensional space, I could take their cross product. Okay, so let's call this vector u, and this vector v. I'm going to take the cross product of u and v. U, the components of u are 2, negative 1, 0. Components of v are 3, 4, 0. And if I take their cross product super quick, for I, I'm going to get 0 minus 0. That's 0 for the I component. For j, I'm get 2 times 0, that's 0. Minus 3 times 0, that's also 0. Okay, what about the k? The k is the only component that's not 0. I'm going to get 8 minus negative 3. 8 minus negative 3 is 11. Okay, notice the fact that we got zeros for these first two components, it's not just a coincidence, that's a pattern. Whenever we have zeros in this last column and we're taking a cross product, when we get our I component, we're multiplying by 0, so we'll get 0 up here. Right? When we're calculating our j component, we're multiplying by the zeros in that last column, so we'll get zeros for our j component. The only component generally that need not be 0 is the k component. Okay? And because whenever we embed two-dimensional space into three-dimensional space, because we'll always get that 0 as that last component, that z value, whenever we embed two-dimensional vectors and three-dimensional vectors and take their cross product, the first two components will always be 0. It's just the last component that will not be 0. Okay, this is the only value that will not be 0. That's going to be important in a moment. And so the area is the norm of the cross product, which is square root of 0 squared plus 0 squared plus 11 squared, which is just 11. Notice the only number that was important in this calculation in finding that area, the zeros didn't contribute anything, right? It's just the 11. And if I square 11, then take the square root, I just get the same thing again. Okay? Now, you got to be a little careful here. If it was a negative 11 and I squared it, and then take the square root, I get a positive 11. Okay? But still, only this last number matters. How did I get that last number again? I multiplied these two numbers together, and then I subtracted what I get when I multiply these two numbers together. What does that look like? That looks a whole lot like a 2 by 2 determinant, right? It turns out that that's a general rule. Rather than going through all this work embedding the two-dimensional vectors into three-dimensional space, if I just take my two vectors and put them in a matrix, and then take the determinant of that matrix, I get what I want. 8 minus -3, that's 11. It's the area of the parallelogram. And again, that's not a coincidence. The 2 by 2 determinant gives us the area of a parallelogram determined by the vectors in the columns of the matrix, okay, or the rows of the matrix. Remember, the transpose of the determinant of a transpose is equal to the determinant of the original. So you could interpret it either way. The area of the parallelogram determined by the row vectors of the matrix, or the area of the parallelogram determined by the column vectors of the matrix. All right, this is a really important observation, gets at the heart of what the determinant is actually telling us and why it's actually useful. A 2 by 2 determinant gives us the area of a parallelogram in two-dimensional space. Now, that's just not quite true, just a little bit off, because it's possible that the determinant could be negative. An area can't be negative, right? If you take the absolute value of the determinant, it will give you the area of the parallelogram in two-dimensional space. Okay? And that, as it turns out, is going to be really important. So let's let A equal a matrix with two columns. V1, V2. Let's let A be a 2 by 2 matrix. Then the absolute value of the determinant of A is equal, let me write it this way, and the absolute value of the determinant of A is the area of the parallelogram determined by vectors v1 and v2. In R2.